All right. So let's just catch up with where we are. We are trying to solve exponential equations. Exponential equations are equations where the variable is in the exponent. So you might have something like 10 to the x equals 1,000. We practiced solving problems like that last time. This you can solve without a calculator. But if we have 10 to the x equals 2,000, for this, we need logarithms to solve. We said that we can convert 10 to the x to logarithmic form. This would be log of 2,000 equals x, and then use our calculator to help solve this. Okay, but for today's class, this works. The technique that we use works if we have exponential expressions with base 10. But what if we have another expression? What if we have 3 to the x power equals 2,000 and we want to solve for x? We can't use the common log because the common log is base 10, not base 3. So we have to talk about a couple other properties of logarithms that we can use that will help us solve exponential equations with any base, not just base 10, okay? The first topic that we talk about here is the change of base formula. So above, I said we want to be able to solve 3 to the x equals 2,000. And I said we can't just use log for that because log is base 10, but our exponential expression is base 3. Well, one trick we can use is to change any logarithm of any base to base 10 by using the change of base formula. Okay, so change of base formula is used to evaluate logarithms of any base by converting to base 10 or base e. Basically, we have a log button and an ln button on our calculator. We can convert a log of any base to base 10 or base e and then use the calculator to simplify the log. Okay, the rule for converting is given here. Log base b of x equals log of x over log of b, or log base b of x equals ln of x over ln of b. So an example of that, let me go to my original problem. I had 3 to the x equals 2,000. If we convert this to logarithmic form, that would be log base 3 of 2,000 equals x. Now for this part, the log base 3 of 2,000, we can use the change of base formula, either one of these, to rewrite this in terms of the common log or the natural log. Okay, notice we start off with one log on the left-hand side, and then we're dividing 2 logs on the right-hand side. So to go from one log, log base 3 of 2,000, to 2 logs, this would be log of x, which is 2,000, divided by log of the base b, which in this case is 3. So log of 2,000 divided by log of 3. At this point, we would be able to, sorry, I gotta reach over and grab my calculator. We would be able to use our calculators to then evaluate this. Log of 2,000 divided by log of 3. We type that into our calculators. Equals 6.9186. We get a decimal, so I'll round it a couple of decimal places. Actually, let's go for 6.9186. That's approximately equal to x. So where do we use the change of base formula? From, that's not right. Hold on. From this step to this step. Log base 3 of 2,000 is equivalent to log of 2,000 over log of 3. We should also note that we could have used the natural log as well. We get the same answer. Log base 3 of 2,000 is also equal to ln of 2,000 divided by ln of 3. So when we're using the change of base formula, it doesn't matter if we use the natural log or the common log. The one thing that we do have to do, though, is use the same log in the numerator and denominator. So we either have ln over ln or log over log. But you can choose either log or ln to rewrite your expression. All right, so for the next few problems, we're going to look at our practice rewriting expressions using the change of base formula, and then we'll do some problems using the power property of logarithms. All right, you try for all of these, and I'll write the rule again. It's log base b of x equals log of x over log of b. Log of the base is in the denominator, or ln, ln of x over ln of b. Again, you can use either one. It doesn't matter which one, you will get the same answer. When we convert to, or use the change of base formula to convert, we'll then go to our calculators to simplify. All right, so starting with 2, we're rounding 4 decimal places for all of these. Log base 5 of 41. This is log of 41 over log of 5. Okay, or ln of 41 over ln of 5. Again, it truly does not matter. You get the same answer with either of these. All right, if we type this into our calculator, ln of 41 divided by ln of 5, you should be typing this in 2 just to make sure you're getting the same answers as me. This is 2.3074. And just so that we don't forget what this even means, what does this mean? This is telling us that if we take 5 and raise it to the 2.3074 power, that should be equal to 41. So we're solving for the exponent that's going to give us the number we're taking a log of. All right, once you know this rule, it's not too bad. For part 3, log base 8 of 12, that's log of 12 divided by log of 8. When you type this into your calculator, you have to type log, open parentheses, 12, close the parentheses, divided by log, open parentheses, 8, close parentheses. This would give us 1.1950. On to number 4, log base 1.5 of 35. So this is what power would I raise 1.5 to get 35? We do log of 35 over log of 1.5. And again, I just want to keep emphasizing that's the same as ln of 35 over ln of 1.5. And this gives us 8.7686. So 1.5 to the 8.7686 power is equal to 35. Number 5 is a fun one. You'll see we won't even need a calculator for this. Log base 4 of 4, if we use change of base, that's log of 4 divided by log of 4. You divide something by itself, we just know that that equals 1. 1. And ln of e will work out that way too. Remember, ln is log base e. So this would be, you can write it as log of e over log of e, or ln of e over ln of e. Of course, they both equal 1. One very nice note, we might get to this later on in this section, but since it popped up here, we take ln of e, that equals 1. Or if you take log of 10, that equals 1. Or like we saw in part 5, we take log base b of b, that equals 1. The base and the number you're taking a log of are the same. All of these things are equal to 1. All right, so we've learned the first of our 2 important properties. The first one is change of base formula. This allows us to take a log with any base and convert it to the common log or the natural log, and then use our calculators to evaluate. Then our second very important property is the power property of logarithms. The power property of logarithms tells us if we're taking the log base b of some term raised to a power, so we have log base b of m to the x power, we can bring that exponent down and multiply it. This is x times log base b of m. An example of that would be log base 5 of, I don't know, x to the 3rd power. This would be 3 log base 5 of x. You bring the exponent down and multiply the logarithm by it. And that works for logs of any base. So ln of m to the x would be x times ln of m also. Oops. The exponent here comes down here. Okay, and this works for any log expression where b, m, and x are real numbers. B is greater than 0, m is greater than 0, and b is not equal to 1. Those are just our conditions for exponential functions. All right. So in problem, we'll skip number 3. Problem 4, we're going to practice using that power property to rewrite all of these expressions. And really, it's as easy as it looks. We're just taking the exponent and multiplying by it. Log base 4 of 5 to the 3rd power, that would be 3 log base 4 of 5. That's all we're being asked to do here. For part B, log base 2 of 3 to the 2x power, we'll bring that exponent 2x down and multiply by log base 2 of 3. Now for part C, we do want to be a little bit careful here. We have log base 5 of x to the 6 to the x plus 2 power. We want to bring the exponent x plus 2 down. And I'm going to put this in parentheses because we want to multiply that entire expression by log base 5 of 6. Okay, and then for part D, ln of 9 to the 4y power, our exponent is 4y. We bring that down and multiply it by ln of 9. And last one of these, log base 8 of 3 to the x minus 5 power, that's x minus 5, and we're multiplying that entire exponent by log base 8 of 3. So the power property, again, just tells us if we're taking the log of some term to a power, we can bring that power down and multiply by it. And you'll see how this is helpful for solving exponential equations a little bit later. This is just to help us practice doing the property. All right. So now we know change of base, and now we know the power property. Next, we're going to talk about how we can use or evaluate exponential expressions and logarithm expressions using inverse properties of logarithms. So when we have the same base for both the exponential and logarithmic expression, we rewrite from one form to the other by raising the exponent to a power of the same base to undo the log, or taking the log of the same base to undo the exponent. So here we're talking about how exponential expressions and logarithmic expressions are inverses or opposites of each other, kind of like multiplication and division are opposites, addition and subtraction are opposites. If you had a problem where you had like x plus 5 equals 9, you would solve this by doing the opposite. You added 5, so you would subtract 5 from both sides. Okay, to undo a logarithm, you use exponents. To undo an exponent, you use logarithms. Okay, so if we wanted to take log base 3 of x equals, I don't know, 10. Okay, this is a logarithm with base 3. To undo this, we'll raise the exponent to a power of the same base to undo the log of 3. What does that mean? We would do 3 to the log base 3 of x equals 3 to the 10th power. And 3 to the log base 3 of x just simplifies to x, and we get 3 to the 10th. Basically, you have the base of your exponential part and the base of the log being the same, they cancel each other out. Or another way to think of this is if we have 3 to the x equals, I'm trying to think of a number that doesn't work here, 19, okay? Then if I want to solve this, I can take log base 3 of both sides. Log base 3 of 3 to the x equals log base 3 of 19. You might be thinking, that looks worse. Why would we do that? Because of the property we just learned. We can then bring down that exponent and we get x is equal to, or x times log base 3 of 3 equals log base 3 of 19. And log base 3 of 3, we said that's 1. So x equals log base 3 of 19. This is an example of where we're going with this. We're going to take exponential expressions, use the inverse property to rewrite the x, or take the log of both sides, and then use the properties of logs that we learned today, change of base, and the power property to simplify the logarithmic expression that we're left with. All right, some examples of how this works is written here too. So if we have log base 4 of 16, that can be written as 4 to the x power equals 16, and then we can solve the exponential equation. If we have ln of e to the 4th, that can be written as e to the x equals e to the 4th, and we can solve the exponential equation. So you can, again, these are inverses, solve exponential equations by writing in logarithmic form, solve logarithmic equations by writing in exponential form. All right. Did we write these earlier? We wrote something similar to these earlier, but these are the inverse properties that we are going to use to help us simplify. They make our life very nice and easy. If we have log base b of b to the x, that just equals x. We have log of 10 to the x, that just equals x. And if we have ln of e to the x, that just equals x. So write these down. All right, I am going to leave problem 5 for you guys to look at, and we'll jump to problem 6. Look at all this fun, where we use properties of logarithms to simplify the expressions that we have here. So our goal is to solve for the x's. We can use the power property to bring down any powers, and then use those, where are they? Boom, inverse log properties to simplify where we can. First one, A and B are actually very nice. If we use the power property for log of 10 to the 3x power, that's 3x times log of 10. Log of 10 is equal to 1. So remember, log of 10 equals 1. ln of e equals 1. Log base b of b equals 1. Okay, so that's just 1, and then this just gives us 3x. Boom. That's as simple as it can get. Problem B works out pretty much the same way. Log base 8 of 8 to the x, this is 8 times log base 8 of 8, which is 8 times 1. So we get 8. Problem C and D work out the same way. Log base 3 of 3 to the 4y, that's 4y times log base 3 of 3, which is 4y. Log base 9 of 9 to the negative 5th. At this point, you should notice the pattern, and we use the property. This is just going to be equal to the exponent, negative 5. The base here and the base here are the same. You just get the exponent. And then for E and F, these are the same thing, even though they look a little different because we're using natural log. Remember, the natural log is log base E. So ln of e to the y, or sorry, ln of e to the 5y, that's 5y times ln of e, and ln of e is 1. So this is just 5y. Similarly over here, ln of e to the x squared minus 3, the ln of e part is going to cancel out, and you'll be left with x squared minus 3.
So I'm confused. Like, I'm very confused. For B, how did you get, like, where'd the X go?
Oh, I made a typo. That's what's wrong. That's why you're confused. It's not you, it's me. That should be an X.
Oh, so be 8. Oh,
It should be X.
Okay, X.
Yeah,
And then
8 to the X equals X. For all of the rest of them, I think that's the only one that had a typo. But for all of these, you should see that the base of the logarithm and the term that we're taking the log of are the same. So then we just end up getting the exponent. Every single one of these problems just simplifies to the exponent.
Okay, thank you.
X, B is X. Forgive my typo. Thank you for pointing that out, Cameron. C is for Y, D is -5, E is 5Y, and F is X squared minus 3. Just using that property, the inverse property, these all simplify to just the exponent. All right. Now, let's put all of the stuff together. Next section is about solving exponential equations using logarithms. This is our goal. We want to be able to solve these things. Number 7 is solving graphically. We've done solving graphically plenty of times. We want to know how to solve algebraically. So that's what I'm going to jump to. Problem 7 and 8 go through more problems with solving. 7 goes through a problem with solving graphically. Remember, to solve graphically for your equations, you let y1 be one side of the equation, y2 be the other, and then you find the intersection. Example 8, which is a worked example, goes through how we can solve these types of problems using the power property of logarithms. So we're going to look at the solution. We are asked to solve 45 to the x power equals 125. Okay, we want to be able to get the x down from the exponent. We can't just pull it down from the exponent by itself. Like, that's just not a rule we have unless we have logarithms. So we know that if we have log of something to the x power, we can bring the x down. So we're going to introduce logs into this problem. So you start off with your original problem, 45x equals 125. Then we're going to take either the log or natural log of both sides. And 45x equals 125, then log of 45x equals log of 125. Okay? And then what's the whole point of us introducing logs in this problem? So that we can use the power property and bring down that exponent. This would be x times log of 45 equals 125. And then we can just divide. Log of 45 is just a number. So we'll divide both sides by log of 45. And we get x equals, log of 45, or log of 125 divided by 45. Okay. At this point, this is the exact solution. If you're ever asked for an exact solution, this would be the exact solution. We can find a decimal approximation for this if we put it in our calculator. Okay, so from the exact form, if we put this into our calculator and round for decimal places, we get that x is approximately equal to 1.2684. And just like with any equation, you can check your answer by plugging the result back into the original problem. If you take 45 and raise it to the 1.2684 power, notice here it does not equal exactly 125. That's because we rounded that decimal. So when we plug it back in, our answer is going to be off a little bit. But it should be something very, 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 very close to 125, which it is. So this works out. Okay, so let's just revisit those steps again, because for the rest of class, we're going to use these same exact steps to solve our problems. You start off with your exponential equation. Then you take the log of both sides. I want to note here that you could have also taken the natural log. You can say ln of 45x equals ln of 125, and the problem will work out the same way. Then you bring down the exponent using properties of logs. Then you divide, and then use your calculator. So this is what the last couple of classes have been building up to. This process. This is how we solve algebraic or exponential equations algebraically. Let's jump into our own. So problem 9 is kind of broken down nicely for us. We'll do those. And then for problems 11 and 12, they're broken down too. But usually you're just given a problem. You won't be given all of those steps. So we'll do 9, 11, 12, 13, and I think 14 has 3 problems on it, 14, and that'll be the end. But they're all just solving exponential equations using these steps. All right, so For number 9, our problem is 25 times 1.25 to the 8t equals 40,000. Okay, so we're going to start off by taking our original problem. Before we introduce logs, we need to isolate the exponential term. In this case, the exponential term is the 1.25 to the 8t power. To isolate this, we're going to divide both sides of the equation by 25. Okay, so that would give us, I'm going to write out 2 steps. 25 times 1.25 to the 8t equals 40,000. We divide both sides by 25. Then we get, hold on, what's 40,000 divided by 25? 1.25 to the 8t power equals 1,600. Okay, boom. So first step, you want to isolate the exponential term. You may need to divide like we did to get the term isolated. Sometimes you might need to add or subtract, but get the term with the exponent by itself. Once you have the term with the exponent isolated, then step 2 is to take the log of both sides. So we'll have log of 1.25 to the 8t equals log of 1,600. All right, on the left-hand side, we can use the power property of logarithms to bring down that exponent, 8t. So we'll get 8 times t log of 1.25 equals log of 1,600. Then we want to solve for t. T is being multiplied by 8 and log of 1.25. We'll divide by those two things. T would be equal to log of 1,600 divided by 8 log of 1.25. All right, woohoo! This is our answer for t. This is the exact answer, but we want to come up with a decimal approximation, rounded to 4 decimal places. Now, when you type this into your calculator, I want you to be very, very careful. We need to, if you look at this, in our denominator, we have 2 terms, so we need the entire denominator to be in parentheses. When you type this, you should type it as log of 1,600 divided by, open parentheses, 8 times log of 1.25. Close both of the parentheses. Some people also like to do this in 2 steps. You can do log of 1,600 divided by 8, and then log that divided by log of 1.25. You can do it in 2 steps if you want to, but this is how you do it all in 1 step. All right, so let's type this in. Log of 1,600 divided by 8 log of 1.25. We get t is equal to 4.1329, or approximately equal to this. And then how do we check our answer? We go back to the original problem, which was 25 times 1.25 to the 8t, and where t was, you type in 4.1329 and type this into your calculator. It should be approximately equal to 40,000. Hold on. All right. This is approximately 40,000. So if you put it in, you get 40,003. Real, real close. All right. Now this one was a little bit different because we had an extra step in the beginning. We had to divide both sides by 25 first to isolate the exponential term. Then once that's done, take the log of both sides, divide, and then type the result into your calculator to get the decimal approximation. All right. Same techniques are going to be used for examples, for the next few examples. Now, We have two different methods that you can use to solve this one. I find method 1 to be easier most times, but some people might like method 2. Method 2 is to use the change of base formula. So if you want to solve using change of base, you still need to isolate your exponential term, but instead of taking a log of both sides, you would rewrite the expression to logarithmic form and then use the change of base formula to solve the logarithmic equation. All right. For the next problem, we'll solve it that way, and then I'll show you an example where we solve both ways, and you can just choose whichever method you want. I won't ever tell you you have to use one or the other. They'll get you the same answer, so you can choose which one you want. Okay, so we're going to solve number 11 using the change of base formula. That's the second method. Here, if we have 3 to the x equals 25, our exponential expression is already isolated, so there's nothing to do there. We have 3 to the x equals 25. Then using this method, instead of taking the log of both sides, we will rewrite this in logarithmic form. So our base will be 3. We have log base 3. We're taking the log of 25, and that equals the exponent, x. So this has helped us solve for x. To calculate log base 3 of 25, we're going to use the change of base formula. By change of base formula, this would be log of 25 divided by log of 3. And then from here, calculator. Log of 25 divided by log of 3. That would be 2.9299. And that's it. Okay, so in order to use this method, instead of taking the log of both sides, you need to convert from exponential to logarithmic form. If you, which you should be, you're going to have problems where you have to convert back and forth between the two. You're really good at converting to logarithmic form, then boom, logarithmic form, change of base, calculator. 3 steps. And of course, we can check our answer here. We do 3 to the 2.9299 power. It is approximately equal to 25. So it is correct. All right. Let's keep rolling. So for problems 12, 13, and 14, you're just given an exponential equation. You're asked to find the result using rounding 4 decimal places. You can use either method. For 12, I'm going to show you how to do this using both methods. And then going forward, you can choose which one you like. All right, so we have 2 to the x power equals 17. I'll do method 1 first. That's where we use the power rule. The exponential term is isolated, so then we take the log of both sides. Log of 2 to the x will be equal to log of 17. Then we use the power property to bring down the exponent. X times log of 2 equals log of 17. Then we divide both sides by log 2. X equals log 17 divided by log 2. At this point, we will need to go to the calculator. Okay, before we do that though, I just want to show you how method 2 will get you to the same spot. For method 2, we need to convert this to logarithmic form. Our base is 2, so we'll have log base 2 of 17 equals x. And then from here, we can use the change of base formula. Log base 2 of 17 would be log of 17 divided by log of 2. And then look, we have the same thing for our final answer. When we put this into our calculator, log of 17 divided by log of 2 is 4.0875. So that's our answer. And again, you can pick whichever method you prefer. All right. Any questions about the 2 methods? The next 4 problems are just going to be us doing this over and over and over. All right, I'll try to go back and forth between the two methods so you can see both. But for every problem, I'll just pick one method to do it in. I won't do both of them. For 5 to the 3t power equals 200. Now notice here the exponent is 3t, so we'll have a little bit more work to do. If we use method 1, we can just take the log of both sides. Log of 5 to the 3t power equals log of 200. Remember, you have to do this on both sides of the equation. Then bringing down the 3t. 3t log of 5 equals log of 200. And then dividing by t. Log of 200. I'm sorry, dividing by 3 and log of 5. Log of 200 divided by 3 log of 5 equals t. And we'll put this into our calculator. Log 200 divided by, open parentheses, 3 log of 5 is 1.0973. We will check our answers. If you take 5 and raise it to the 3 times 1.0973 power, make sure you get something that's close to 200. When I put this in, I got 199.95. So yes, that is approximately equal to 200. So it checks out. All right. Now you try, as the directions say. For problem 14, this is the last one in 3-7. There are 3 problems here. 6x equals 6 to the x equals 100, 7 to the 4x equals 400, and 8 to the 5x equals 678. I want you guys to take a moment to try to solve these problems. You can use either method, round 4 decimal places for your final answer. And I'll give you a few minutes to go over this, and then we'll review the answers together. All right, for problem number A, problem letter A. Louise said he got 6 to the 2.5702 power. The answer would not be written that way. It would just be the x part. So it would be x equals 2.5, what did you get? 2.5702. That was correct, but you only need to write x equals 2.5702. The entire way that you wrote it, though, is how you would check. But very good. We take the log of both sides here. We have log of 6 to the x equals log of 100. So x times log of 6 equals log of 100. And then x would be equal to log of 100 divided by log of 6. Of course, you can type this into your calculator. I just want to note, anybody out there recognize that log of 100, we can simplify that. That's equal to 2. So this is 2 over log of 6. You don't have to write it this way. You can just type it into the calculator. You get x is equal to 2.5702. That is the correct answer. So very good, Luis. Does anyone want to share the answer that they got for part B? 7 to the 4x equals 400. If anybody got one, you can just tell me what you got for x.
0.7698.
0.7698.
Yeah.
Yes, I got the same thing. All right, so this would be log of 7 to the 4x equals log of 400. 4x log of 7 equals log of 400. Then we divide. X is equal to log of 400 divided by 4 log of 7, which is 0.7698.
So I was trying to do this one the other way, and I think I'm just completely lost because I just got log of and a tiny 7, then 400 equals 4x, and then I had no idea what to do.
You need to rewrite that using change of base formula. So if you don't know how to do that method, use this one. You can use either one of them. But for the other method, From 7 to the 4x power equals 400. You said you got log base 7, that's how that's read, of 400 equals 4x. Change of base formula would be log of 400 divided by log of 7 equals 4x. And if you divide both sides by 4, you get the same exact answer. Log of 400 divided by 4, log of 7 equals x. You do not have to use that method though. If you don't understand it or you get stuck, use the method that works for you. So hopefully one of them works. You are allowed to use either one.
Thank you.
Okay. But for the second method, after you convert to exponent or logarithmic form, you have to use change of base formula. That's the key there. All right, what about part C? Did anybody get an answer for part C that they want to share? All right, I'll get one. So let's do this one using the second method. If we convert this to logarithmic form, we'll have a log base 8 of 678 equals 5x. Log base 8 of 678 can be written as log of 678 divided by log of 8. That's using the change of base formula. And then we get that that's equal to 5x. Someone shared an answer for this one. You got 0.627. All right, let's see. If we divide this by 5, oh my God, who put a part D down there? My bad, y'all. I didn't know there was a D. We'll do that one though. Log of 675 divided by 5, log of 8 equals x. Let's type this in and see if I get the same answer as Ashley. And I did. So x is equal to 0.62. We went around 4 decimal places though, so I'll go 66. 0.6266. Yes, that's correct.
How did you put it in the calculator again? Like with the open parentheses or something?
So when you type in logs on your calculator, most of the time a set of parentheses will open up anyway. So if it's log of 675, close that parentheses, then divide it by open parentheses 5 log of 8.
Okay, thank you.
So just make sure your entire denominator is in a set of parentheses. All right, and for the last one, someone got x equals 2. I hadn't even scrolled up enough to solve this one, so let's try it. If we take the log of both sides, this is using method 1. Log of 5 to the 3x power is log of 15,625. Then 3x times log of 5 equals log of 15,625. And then if we divide, x is equal to log of 15,625 divided by log of 5. And if we put that into our calculator, let's see. Log of 15,625 divided by, oh, I missed the 3 here, sorry. 3 log of 5. We get 2. Very good. So good job, Louise. All right, so this ends section 3.7. The big thing we're supposed to take from this section is what we've been doing for the last 7 examples, how to solve exponential equations algebraically using either the power property of logarithms or the change of base formula.